Hello students, in the last video we have discussed about pumping lemma for context-free languages. So in this video we'll discuss about closure properties of context-free languages. Same closure properties we have discussed even for the regular languages also, right? So let me go with this. We have so many closure properties, but CFL are not closed under, CFL are closed under union, concatenation and clean closure. What does it mean? Of course, it is also closed under reversal, homomorphism, and inverse homomorphism. What does it mean by closed under? Right? Let me tell you. See, let me tell you the statement first. Closure properties. If L1 and L2 are two context-free languages, right? L1 and L2 are two context-free languages. Then, if you are saying that the CFL are closed under union, then the L1 union L2 must be a context-free language. If you are saying that it is closed under context-free language, union is closed under context language, then it must be a CFL, right? So we have theorems and proofs for it. The CFL are closed under union, concatenation, and clean closure. Means you take any two context-free languages, the union of two context languages must be CFL. And if you take any two context languages, the concatenation of this, of course, we'll give some example for this, right? And what is this? But not closed under intersection, complement, and difference. So it's very easy to remember the CID properties. Okay, complement, intersection, and difference. So complement, we will be having a conflict with the concatenation, but of course, it's very easy to perform the concatenation of two CFLs or two FCFJs, but not with the complement, right? So we'll give the proof for this. What does it mean by not closed under? Okay, what does it mean by not closed under? Means you take any two languages, L1 is CFL and L2 is CFL, as the it is not closed under intersection and difference. Means intersection means the L1 intersection L2 may or may not be CFL. We cannot give guarantee or we cannot give conclusion overall, right? For some languages, intersection may be CFL. For some languages, intersection may not be CFL. But for here, for all the languages, the union must be CFL, but not like here, right? So that's exactly how. So let me explain this with a some examples. First, closure properties union. How this will be closed under union. So let L and M be CFLs with grammar G and H. Assume that G and H have no variables in common. Do not affect the language. So make sure that the grammars doesn't have the same variable names. If so, just rename it, no problem. Then how can we do this concatenation? Assume that we have a grammar for a power n, b power n, right? L equivalent to a power n, b power n. We have already discussed the grammar for this, like a, s, b, r, epsilon. I'm assuming that this is s1, right? Okay, let me go with this s only, so that you'll come to know about it exactly. What is the first point here, right? So A is B, and assume that we have another grammar L2. So where we are going to have A power 2n and B power n for every A. For we should have two B's for every B. Then you can write the grammar like this: A, S, B, or epsilon. You are going to have like this. Now we are having the same two different grammars. This is G and H, but as we are having the same name, just rename it. I'm renaming it as S1 and S1, S2 and S2. No problem with that. Then how to perform the union here? We have to take L1 union L2. Means perform the union of these two grammars. It's very easy, guys. Introduce a new non-terminal yes by saying that either S1 or S2. Then you can write S is A S1B, sorry, S1 is or epsilon, and S2 is A S2B or epsilon. That's it. Like that, if you are given any two context-free grammar, just introduce a new non-terminal and by writing the existing non-starting symbols as or. That's it. So this we have proved it. The union is also a context-free grammar, right? It is also a CFG, so automatically it is CFL. Let me go with the concatenation. right? So let me take the same notations here. Let me explain concatenation. Same S1 S2, how to write it. So here take the same examples whatever we have taken here, right? Then just introduce a new non-terminal S by perform the concatenation of S1 and S2 and concatenation. Then what is the S1 we have earlier? Like you can take A S1 B or epsilon. What is S2 we are having here? A S2 A S2B or epsilon. Just we have to perform the concatenation, right? So we have taken here union. Union means just or, concatenation means and. Then let me go with the clean closure. How we have to do it? So I'll start by using the G like this. See, clean closure we are going to do it with by introducing a non-terminal. S tends to the grammar non-terminal, then you have to write it. See, clean closure means what? If you are having A, we have to make it A star, means any number of A, 0 to infinite. So if it is S, we have to write S star. How to write the production we have discussed. If it is S tends to A, we have to take only one time. If you want to do it repeatedly, you can just write down the recursion like this. S tends to AS, right? S tends to AS, like that. Single A can be taken any number of times. S tends to AS, like that. But make sure that there is a termination condition. That's why I'm writing epsilon. Same. For example, if you have a grammar, whatever we have taken, L1 equivalent to, earlier we have taken it, A power n, B power n, such that n greater than or equivalent to 0. So what is the grammar we have for this? S tends to A, S, B or epsilon. Then how to perform the clean closure of this? Means L1 star, you have to write the G star. How to write the G star? Just introduce a new non-terminal X. So what is the existing non-terminal S? So you can write S tends to A, S, B or epsilon. But how many times I can take this grammar? Only one time. But if you want to take it infinite number of times, simply you can write here X. So this is the clean closure of the grammar. You can do that. So this is how it is going to be, right? So it is not closed under the intersection, right? Let me explain this. So we have already proved that 0 power n, 1 power n, 2 power n is not a CFL with the pumping lemma in the last one. Okay. So let me go with this. Okay. And we have 1 power n, 0 power n, 1 power n, 2 power I. So this is a CFL, right? And L2 and L3, 0 power I, 1 power n, 2 power n. This is also CFL. Okay, let me explain this with example. Don't worry, let me just erase all. Okay, don't worry about these examples whatever I mentioned here. Let me just go with the other examples, guys. So other means same. I'll write in a different way. That's it. So for example, you'll be having like this: L equivalent to A power n, B power n, C power m, such that n greater than or equivalent to 0. We have proved that this is CFL. We have constructed the PDA. For every A push it, for every B pop the A. We don't have any dependence here. What is the language we are going to have here? So you'll be having A, B, right? And any number of C's, A, B, C, or A, B, B, C, or A, B, B, C, C, like that. Number of A's must be equivalent to B, but not worrying about the C. Number of A's must be equivalent to B, not worrying about the C. Number of A's must be equivalent to B, not worrying about the C. This is L1, assume that. Then we are having L2 like this. L2 equivalent to A power m, B power n, C power m, such that n comma m greater than or equivalent to 0. So this is also CFL, where the A and C are equal, but we are not worrying about the B. Can be anything. This also we have discussed, guys. So means we can take it AC equal or ABC. AC are equal, or AABCC. AC are equal, or AABBCC. AC are equal. Then this is L2 CFL. Then take the L1 intersection L2. What are the common symbols? AB, AC not common. ABC is common, right? So what is another one? AABBC not common. AABBCC is common. AABBCC. Take all the strings which are satisfying both the conditions L1 and L2. AABBCC, triple A, triple B, triple C, or 4 A's, 4 B's, 4 C's. Here AB must be equal. Here AC must be equal. In the common, ABC must be equal. So what is the language we are going to have in L1 intersection L2? It would be A power I, B power I, C power I greater than or equivalent to 0. In the last video, we proved that this is not a context-free language. There is a reason we are saying that intersection of two CFL may not be the CFL. This is CFL, this is CFL, but intersection is not CFL. So some CFL are not closed under intersection, right? Sorry, CFL are not closed under intersection means intersection of two CFLs may not be CFL sometimes, right? Same way you can go for the difference also, right? So you can take it, assume that L and M, okay? How can we do this? Assume that we have two languages, right? So if our alphabet is A comma B, right, then the sigma star would be any number of languages, all the strings possible with the A comma B. Then you take complement if it is not closed under complement, right? Complement means sigma star minus L. So from the universal language, if you remove the L, the resulting language may or may not be CFL, that we don't know, right? Same way, difference means you're having L1 is CFL and L2 is CFL, but L1 minus L2 may or may not be CFL, that we cannot do it. So take some languages and you can check with that, right? So whether it is closed up, but we have already given the proof for intersection here. So same way, take some languages like A power n, B power n, and you can give it. Let me go with this. What's the problem? So if you are having like this L1 equivalent to A power n, B power n, C power m, such that n greater than n comma m greater than or equivalent to 0, where A, B are equal, right? Then let me take L2 equivalent to A power n, B power m, C power m, such that let's see B power m, C power p, such that m not equivalent to p. B and p, B and c are not equal. Then here BC may or may not be equal, but BC must not be equal. So here it may or may not be equal, here must not be equal. So from L1 minus L2, here may or may not be equal, but here must not be equal. So from may or may not be, if I remove all not equal, then what we are going to get in the L1 difference L2, A power n, B power n, C power p, such that n must be equivalent to p. M must not be equivalent to p, we have removed. So B, C must not be equal, we have removed. So BC must be equal. Here already AB are equal. Then automatically what will be happen? The number of A's must be equivalent to number of B's must be equivalent to number of C's. So just now we have proved that this is also not a context-free language like that. You can just explain this with a simple grammars and you can write the statements. Okay. So in the next video, we'll discuss about deterministic context-free languages.